Hi everybody. Today we're going to start a really interesting part of chemistry, and the topic now is chemical bonding. And the things that we're going to do today is we're going to look at the objectives first, and then we'll move on to the first objective, which is why do chemicals bond? Why do atoms bond to one another? Sometimes at least. And then we'll look at the two main types of bonds, ionic and covalent. And then we'll look at some of the properties of compounds and when they make solutions in water, and we'll consider a couple of different types of compounds. And then after that, we'll look at a really important concept, which is called electronegativity, which is the attraction for electrons, how much an atom really wants electrons. And then the last thing is something called delta En, which means difference in electronegativity. And we will look at how much one atom likes an electron compared to another atom. We want to be able to define what a chemical bond is. Next, we want to very, very briefly explain why most atoms form chemical bonds. A little bit of time looking at ionic and covalent bonding and the properties of compounds, and we'll explain why most bonding is neither purely ionic or covalent, and then we'll look at classifying the different bonding types according to electronegativity differences. So the first thing is, what is a chemical bond? And the definition for chemical bond is the electrical attraction between atoms. Um, why? Why do atoms do this? Well, they do this, generally speaking, to obtain a lower energy, or at least for the universe to obtain lower energy. And sometimes there are some other factors involved here. Now, so if you look at this diagram, here's a couple of atoms before they bond, and here are those atoms after they bond over here. And they start off with a relatively high amount of energy, and when the reaction is done, they have lower energy. So we will look at that in more detail later, but for right now you just say, what is a chemical bond? It's the attraction between atoms. And secondly, why do they do this? To obtain lower energy. All right, well, there are two types of bonds, and two main types of bonds, and they are called ionic bonds and covalent bonds. You know that there are cations and anions, and you might recall that we spell the word cations, Ca plus I-O-N-S, and we spell it with a plus instead of a T because that reminds us that a cation has a positive charge. So if you look over here at this example, here's calcium chloride. Here's an atom that has a negative charge. It has gained an electron, and here's an atom right here in the middle that has a +2 charge, and so it's a cation, and to get to be a positive charge it must have thrown away two negatives, two electrons. And over here on the right there's another atom that has a negative charge. It's gained an electron as well. So the second type of bonding that we'll look at is called covalent bonding, and covalent bonding is due to shared electron pairs between atoms. So if you look at this example right here, here's an atom and there's an atom, and then right here are two electrons, and they are shared electrons, a shared pair of electrons. This is called a covalent bond right here. So these two atoms put together, bonded together like this, we call that a molecule. So let's take a look at the properties of ionic and covalent compounds. So you understand the concept here of a formula unit and a molecule, and these are, and you can see the atoms, but in real life, you know by now that atoms are way, way too small to see. But what about if you have a compound, if some sort of compounds that you want to decide, are they ionic or are they molecular compounds on a larger scale? Well, one thing you can do is you can put them in water, and you can make an aqueous solution. So ionic compounds conduct electricity in aqueous solutions. Molecular compounds don't conduct when they're put in an aqueous solution. And by the way, things that do conduct are called electrolytes. And you've heard the term electrolytes in regard to, say, Gatorade and things like that. So what I have here is some distilled water, and right here I have a conductivity apparatus. There's a light bulb, and then there are two electrodes that go here, and if electricity will flow through a solution, this light bulb should light up. So I'll set this right here, and I'll take some water, distilled water, so it's very pure, and I'll put some in this beaker, which I've labeled molecular. So I'll put a molecular compound in there before too long. And then this beaker is labeled ionic, so I'll put an ionic compound in here, and we'll see what happens. Well, the first thing is, let's just test this and see if water conducts electricity. So I'll just take and put the electrodes into the water and see if the light bulb comes on, and it does not. And that means water is not conducting electricity, and that means that water is a non-electrolyte. And that also probably means that it is a molecular compound. So what we can do is take an ionic compound. So here's an ionic compound. It's I've got potassium chloride. If you look at the periodic table, oh, I have one right here. Potassium is from this side, and chloride is from this side of the periodic table, so opposite sides. And you should know that there's a pretty good chance that there will be ions made here. And I'll take some of this potassium chloride and put it in solution. And this, and I'll mix it around just a little bit. And so an ionic compound in water. Let's see if the light bulb turns on. And here we go. Oh, yes it does. So what we're saying is that we've put an ionic compound into the water and now it's conducting electricity. Let's try the same experiment, only using a molecular compound. So this time I'll take C6H12O6, which you probably remember is glucose. So C6H12O6, everything is from the right side of the periodic table. But we'll get into that in more detail later. Just say this is a molecular compound. So I'll put it into the beaker labeled molecular and dump some in there. And I will mix this up. Mix it, molecular compound. Well, let's see if it conducts electricity. Here we go. And nope, doesn't do it. So this is not an electrolyte. The molecular compound is not an electrolyte. It's not conducting electricity. We'll do an experiment with this very early in this unit. The next thing that you should probably write down is that ionic compounds have high melting point and boiling points. In other words, it's really hard to take an ionic compound such as potassium chloride and melt it. So you can put some of this in a frying pan at home and turn on the burner full blast hot, and it would never melt. But if you took a molecular compound such as water or such as C6H12O6, these two compounds, you should be able to make them melt. Water is probably melted already when it comes out of the tap, but you could take some ice and put it in a frying pan and you could easily melt it, and you can boil it too. It's a molecular compound. Same thing with sugar. The problem with sugar is, when you try and melt and boil sugar, is that it tends to burn pretty easily, and so it's hard to, that kind of masks the melting and boiling. The next thing is that molecular compounds are usually softer and ionics are harder and often brittle. So any kind of ionic compound is probably like, if you think of a crystal, or if you think of salt crystals, if you took a hammer and hit them, they would shatter all over the place. Molecular compounds are things like rubber, oil, things like that. They're softer type of compounds. Furthermore, many molecular compounds are even gases. So anything that you're breathing right now, O2 and CO2 and N2, anything that's in the air right now that you're breathing is almost certainly a molecular compound. Electronegativity is the next concept. We just write En often, and this is defined as an atom's attraction for electrons. Metals have a low electronegativity and nonmetals have a high electronegativity. So if you have your periodic table with you, you should probably make a note. Well, actually we'll include these. Everything on this side of the stair step, right? This is the stair step that you've seen many times. Everything on the left side is a metal. Everything on the right side is a non-metal. Metals typically have a low electronegativity, so that's here. Metals have a low electronegativity, and non-metals typically have a high electronegativity. If you look at this periodic table on the right, it's kind of neat. It's three-dimensional, and so you can see that the elements on the upper right part of the periodic table are shown as like skyscrapers because they have a really high electronegativity. Fluorine has the highest electronegativity on the periodic table. Now, one thing you have to remember is this periodic table doesn't show the what? It doesn't show the noble gases right here, because noble gases are exceptions. They do not have a high electronegativity. They do not want more electrons. They already have a full outer shell. So they're good. So fluorine right here, that's the one that has the highest electronegativity. And if you look at the periodic table here, way down in the bottom left, these have the lowest electronegativity. Matter of fact, they would almost rather give away electrons. The metals would typically rather give away electrons. Non-metals really want to gain electrons. Do you have an ionic or a covalent compound on your hands? Well, we can use this concept of delta En, and this is the delta symbol. It's a Greek letter, which means difference in this case, difference in electronegativity. So if you take two atoms and you just subtract, that's difference, you can figure out their delta En, their difference in electronegativity. For example, if you took, lithium over here, there's lithium right there, and you took chlorine, atoms. Chlorine on the right side. Lithium has 1.0, chlorine has 3.0. The difference is 2. So their delta En is 2. Now let's look at this. Let's consider lithium chloride. Its delta En is 2. Where does that fit here? Oh, that's greater than 1.7. That means lithium chloride should be an ionic compound. And we'll also sometimes look at this concept here, which is percent ionic character, but this is much less commonly used than just saying, you know, the basic bond type. But percent ionic character means, is it really, really ionic, or is it not so ionic? And so usually the cutoff of 1.7 means that that a compound has greater than 50% ionic character. So the other two types of compounds that we'll look at are both covalent compounds. One is called polar covalent, and one's called nonpolar covalent. And polar covalent is sort of in the middle between ionic and nonpolar covalent. And its cutoff points are 0.3 and 1.7. So if you could write those numbers down, all these numbers right here, that would really help in the future. Now, nonpolar covalent means that there aren't poles, there aren't positive and negative parts of these atoms, and they have a delta En of less than 0.3. So if you look at two compounds, say, oh, let's see, here we go. If you had boron and silicon, if they bonded together, their delta En would be 0.2. So they would be, that's less than 0.3, so they would make a nonpolar covalent compound. Or if you wish, you could take these numbers up here and put them onto a number line as well. And here's the delta En of 0.3, here's the delta En of 1.7, and those separate the three different types of compounds. Let's do some examples, shall we? So here's the exact same things that we were just looking at before, this periodic table which has electronegativities. And here's that same table, I just made it look a little bit different with the cutoff points. And here's the number line right here, so you can use any of these, all of these things. So let's do a couple of examples. Let's say you had nitrogen bonded with oxygen, N and O. You look up here, let's see, N, there you are. 3, O, there you are. So if those two bonded together, a nitrogen atom and an oxygen atom, what kind of compound would you get? Would it be ionic, or would it be polar covalent, or would it be non-polar covalent? Well, what do you think? What's the delta En? What's the difference in electronegativity? Difference is subtraction, so the difference is 0.5. Now where does that fit here? 0.5? There it is. So nitrogen and oxygen will make a polar covalent compound. Let's try oxygen and cesium. So cesium is way down here, so 0.8, and oxygen is 3.5. The difference is 2.7, isn't it? I think it's 2.7. And where does that fit? Oh, that's more than 1.7, so that would make an ionic compound. So if you had oxygen bonded to cesium, ionic compound. And that is today's lesson. I hope you had a good lesson today, and if you have any questions, make sure you stop in anytime.